Welcome to The Sims 2 building building editor. But yeah, really, it's the Reasonend Schemer, the next edition. I'm quite far now. Chapter 7 or something. I'm more than halfway through for sure. So I'm gonna jump in there. Members only, yeah, that were sweet memories. Just a bit more. Okay, yeah. Now we are doing arithmetic, I think. So maybe here. I go here. And then I only have one screen. Oh, this would be too many memories. That's so crazy. I actually can't do that. But I like this decompressed chess. Yeah, I'm gonna listen to this. All right. Okay, and now this one I can delete and default. Okay. All right. Okay. We are talking. I'm missing the Evans thing or the Reasonend Schemer thing. Oh, okay. All right. Okay, let's go. So I see a gazelle and a monkey and an elephant. Oh, he's already he ate like for like 26 bowls of pasta, spaghetti, and cake. And there's also some like cake accessories. The monkey is having this trolley, and they're actually sort of flying. I don't know, like I guess they come flying in like into the kitchen, like here. And so this elephant is he already ate too much, I think. But they actually bring a bit more. So it's a picture of gluttonously and glutton society, and still these animals are like happy to no, okay, either way. What is the value of run 10 x y r o? Wait. 1 sec. I'm one chapter too far. A bit too much. Yeah, a bit too much. I'm at chapter 7. Okay, a bit too much. Okay. So this elephant is also not doing so great. His kitchen blew up or something like that. Okay. Is 0 a bit? Yes. Is 1 a bit? Okay, yes. Is 2 a bit? No. A bit is either 0 or 1. Which bits are represented by a fresh variable? 0 and 1. I don't. Where does this come from now? But yeah, okay. No, if I also constrain it to be either 0 or 1, I suppose. If I say it's a bit. Here's bit x oro. So that takes an x and a y, and r is the output. So three things kind of. like in logic programming. And that's the truth table of bit XOR bit XOR. So far so easy. Now they say another way to define it is with bit NAND. So I'm supposed to define bit NAND. Okay, let me define bit NAND. Yeah, let's get this training done. Okay, so X, Y, R. Well, actually, you can use Copilot. I don't. Yeah, okay. So it's con D because it's a disjunction. Okay, wait. Let me write it once myself. I think. Okay, so not and wait, for something like this, you can always look at Wikipedia if you code some concept. NAND. Like I don't need to figure out NAND, no. Although maybe it would have been obvious. Okay, so they are not and not and. What? One sec, not and. Also not and. Also yeah, there's only one case where it's false. That is here. Yeah, true. Okay. So X is 0 and Y is 0. In that case, R is 1. Yes, and then one of them is 1, the other, and then this is also 1, and then the other one is 1, and this is also 1, and then both are 1. And in that case, it's not correct, not true. Okay. This is NAND, and then you can define XOR in terms of NAND. They say fresh STU here. Bit NAND. Oops, bit NAND. XYS. Let me think about that. Okay, so XOR means that either of them is true, but they are not both true. So if I say NAND, but I also need to say that one of them is true or something, right? So okay. So NAND XYS. Now S is basically a thing that is 1 for all cases, except for the case where X and Y are both true. Okay. And then another NAND. Now I take SYU. XST, XST, and then finally, yeah, this is quite interesting. Both bit XOR and bit NAND are universal binary Boolean relations, since either can be used to find all other binary relations. Yeah, that's something that you could play through. Yeah, this year is taking me a little bit by surprise. Make 3 fresh things, and then like plug them together, y x y, so they're NAND, then s y u, say xs, and then finally say tu. Okay, I kind of see the structure that we say that x and y are like s is only 1 if x and y are not both 1. So either x or y are 1 now, and s basically is 1 in the case where we say that here's s twice. So it would basically be these cases if it ends up being 1. And then x and y. Again. And we also already said that they are both not 1. They are not both 1. So yeah, I guess now we are basically assigning either of them to 1, and then u2, and then not and r. Yeah, given the case that r is 1, these are both not 1, so one of these was either way, it's fascinating that it works. I leave this at the moment here. Okay, demonstrate this using run. Okay, let's say run xy bit xo xy 0. Yeah, okay, so there's one solution. That is that both of them are 0. There's no... Oh, the other solution is both of them are 1, yeah. Yeah, and these are the 2 solutions we get. When is 1 the value of r? 1 is the value of r if either this one is 0 and this is 1, or the other way around. Like this. Yeah. Okay, what is the value of run x, y, r? Yeah, no, this is basically the truth table. Yeah, it's like if you ask for the world, you get the world, kind of. That's a logic programming thing, I think. Okay, then here bit and bit ando. Here's bit and ando. Okay, that's easy for me. X, Y, R. Oh, isn't it simpler? Okay. Okay, x0 and y0, in that case r0. Then either of them is 1 and it's still 0. And then both of them is 1. And that makes this one 1. Another way to define bit ando is to use bit NAND and bit notto. Bit not o, bit notto. That works like that, right? XR, okay. Oh, That's okay. This is cute. No, bit. What the hell? That was funny. Okay. Define bit noto in terms of bit nando like this. Damn. In that case, it's nando. He turns 1 if it's, yeah, and then 0 if it's, that's true. Good, if I say bit nando, and then here I say q is 1, that was not correct. Bit nando? Wait, one sec. So this doesn't have enough arguments. That was bit noto. 0 and 1, yeah, true. Wait, 0 and 1. So Q is 1 and R is 0, yeah, sure. Okay, that's not too. Okay, now define bit ando in terms of bit noto and bit nand and bit ando XYR. Okay, I'm gonna think about it. I'm gonna attempt. So not NAND. So not NAND. Okay. Bit nando XYS and then bit noto SR, yeah. Okay, that's how this works. Yeah. Bit noto itself is defined in terms of bit nando. Yeah, not NAND. That makes sense right now. Demonstrate ando. Okay, run everything XY bit ando XY1. Okay, there's only one solution with X and Y above 1. Yeah. Here is half adder. Okay. By the way, since I'm added in pattern matching, yeah, in pattern matching, you write X, Y, R. Yeah, okay, and then it's all the cases. But yeah, it collapses quite a bit down into saying 0, 0, 1. So that's the high level of the pattern matching. 0, 1, 1, and 1, 1, 0. You literally just write down the truth table. And that also still works. Yeah, it would have been the same here. Bit ando. And now you could say this, and then, and this is actually also quite cute, like this. So it's boiled down to 2 cases. Same thing here. Yeah, all these cases would. Oh wait, I do one mistake though. I don't bind them to numbers, the inputs. So wait, here this is actually this different semantic that is not the same. I also need to make them bits first. I would need to narrow them down to bits. If they are bits, then this means 0 or 1, but if they are not bits, then this means anything still. 1, 1. Okay, but I have a different definition for an AND anyway, but yeah. Okay, like this. Yeah. Okay, then half addero, half addero, XYRC. Oh. Okay, so I'm not so deep into like circuit whatever theory of computation or arithmetic or whatever this is. This is a half adder. Okay, half addero. Okay. Y X. So you take 3 bits, and you have an output, I guess. X Oro. So R is saying either of them is true, and then endo. Also this here is the second bit. Also that's the first. No, not the first. But yeah, this is kind of the next bit or something like that. Like this is when you add 2 bits together and they're both there. Then C is basically the 2. This would be 2. This would be 1. 1 plus 1 is 2. So C is basically 1 if the outcome is 2. And so R is the remainder. Yeah. So it's either 1 or 0 right now. Half adder can be redefined. Oh, okay. You could also write half adder just completely like this. Of course, that's true. Okay, so now I run R, half adder, half addero, 1 R 1. Okay, it only works if this is, yeah, if R is 0, yeah, R is just 0. The remainder, when you add 1 and 1 together, the outcome is 2. So C is 2. C is 1. Oh wait, it's still fresh. The Fug. Wait. 0 would have been correct. Oh. Yeah. This is a noob mistake in core.logic. Yeah. Okay. So that was because I didn't combine these into a conjunction, but basically the body of a core.logic goal function basically is a conjunction together. They are allowed to yield goals, but here I just had a function that returned. It returned a single goal, but I need a function that returns multiple goes. Actually, I can also wrap it in a lambda. Pretty sure this would also work. Oh no, this doesn't work. So this takes a argument. Maybe this would work. Ah, no. Okay. Never mind. Okay, I'm gonna yeah, condi or fresh, for example, or the equivalent or something similar is definite. But yeah, now I don't know if I gain anything from the pattern match. X, Y, R. No, I don't think I gain from pattern matching. Yeah, this is not, I don't know, this is not really better. I think this is fine. Okay. Half adero. Okay, this is the truth table again. It's kind of a cool concept. It's just exhaustive search in a way. If you pass fresh variables for the complete thing, you kind of get everything possible still. The space of possible half adero inputs and outputs. yeah. This is yeah. Given the bits x, y, r, and c, half adder satisfies x plus y equal r plus 2 times c. Oh. Yeah. Yeah. Because C is 1 when it's 2, yeah. When both of them are true, then C becomes 1. So yeah, you can write it like this. Okay. X plus y equals r plus 2 times C. Das ist half adder. Okay, here's full adder. That must be something recursive probably. I mean, 2 half adders, okay. A full just means a full word or something, a full byte or something like that, I think. B, X, Y, R, C. W, X, Y, V, Z. Okay, now you make two half adder calls. W, okay, the first half adder call here makes a half adder with X, Y, with X and Y, okay. So W is kind of the carry bit or something like that, I guess. And then XY means that X and Y made a 2. Now I say that I'm gonna take some of the outcomes of this first computation, so to say, I guess. That is taking this carry bit, so whether there was a remainder, then use this B input, and those two to get together, they make R and WC. Okay, so R and WC are now also kind of remainders, and WC means that there is a 2. C, outcome C, okay. Bid XORO XY and this C. So C is even one more. Oh, that one's so that one just says whether there was a 2. Okay. What if both are 2? Then B was 1 and R was 1. But W can't be 1 in that case. This is impossible. Maybe they can never both be true. Shouldn't it say 4 or something like that in the end? These are basically the hidden outcomes. W is the carry bit, and then add the carry bit to B, and R is the remainder, and C is C means 2 times. Wait, I'm gonna write this again like this here. B plus X plus Y equal to R W and Y, W and B. I want to say something like this, but maybe I'm wrong. How can this be the same? How can this be X plus Y is R plus 2 times C? And here I say that, but actually I say 2 times, I say X plus Y. Equal W plus 2 times X, Y, and here's another equation, W plus B equals R plus 2 times this, and here it says XOR, I don't know, XOR. So you know that C is true if both of these are true. That X and Y, they added themselves together without a remainder. How can C actually ever be true? Because B is the remainder. So W is the remainder. Okay. I'm gonna read now. The X, Y, and R and C variables serve the same purpose as in half. At a full adder also expects a carry in bit B. What values are associated with R and C? Oh yeah, maybe they can help me reason through it. Run RC full adder. Oh, full adder. Zero one one RC. Okay, so B is 0, then this is 1 1, so this becomes 1. B is 0. And W is 0, so this is already 0 for sure. That means that R is a given 0 and WZ is 0. These two are 0. R is also only 0, and C is 0. So C is 1, yeah. Yeah, that's the only solution. Okay, now another one. 1 1. Okay, with 1 1 and with 1 1, then this became 1, then R is 1. This is 0 and this is 1. Yeah, 1 1. What is the value of BXYRC? Full adder BXYRC. Okay, yeah, true. I could have done this to understand it as well. I mean, sort of as a tool. Describe full adder. Yeah, it does do that. Yeah. I was right about this. I feel vindicated. But wait, B? So yeah, if B is 1, then R becomes 1. Yeah, true. And then sort of, yeah, if any of those is 1, R is 1, and if a pair of them is 2, then R should become 0. It's kind of counting. Yeah, of course. Adding is counting how many ones you have or something, actually. Oh, that's how you get... Yeah, I guess. It's one way to get more and more numbers now. Counting how many ones you have. Yeah, the same thing keeps on going, I think. But yeah, it would require like quite a bit more nesting. Okay, what is a natural number? A natural number, I think, goes up from 1 equal, greater than or equal to 0, and is 1, 2, 3, 4, 5, and so forth. Is an integer greater than or equal to 0? Are there any other kinds of numbers? Is each number represented by a bit? Is each number represented by a bit? No, each number is represented by a list of bits. Okay. So yeah, you can't. So obviously, a bit is only 0 and 1. I need more than a 0 and 1 to represent numbers. Which list represents the number 0? The empty list? Correct. Good guess. Does the singleton 0 list represent the number 0? No. Each number has a unique representation, therefore singleton 0 cannot also be 0. 0 is already 0, okay. 0 does not represent a number. The singleton 0 that just doesn't represent a number. Okay. Which list represents 1 times 2 to the power of 0? That is the number 1. Yeah, probably this then. Ah, nee, like this. Okay. This is the number 1. Okay. It's kind of like 1. Yeah, okay, but no, it makes sense that this would be the 1. Okay. Yeah, 0 is kind of over-determined or something, because I feel like this would be just as natural to say that this also is 0, but this is 0. Okay, which number is this here? This is the list 1, 0, 1. Okay, so this is 1 plus 2 to the power of 0. No, 2 to the power of... Yeah, okay. So 1 times 2 to the power of 0 makes 1, then 0 times 2 to the power of 1. And then 1 times 2 to the power of 2. So 4 times 1. Okay. 4 plus 1 is 5. Yeah, okay. Because the value of this... Yeah, okay. Correct. Which number is represented by this? This is the same, but I also add a 2. So I come to 7. Also correct. Which list represents the 9? Okay, so you can make the 9 into an 8 plus a 1. And an 8 is 2 to the power of 3. 1 looks like this. This is 1, 4... 1, 2, 4, 8. Okay, like this. This is 9. Yeah. Yes, how do we represent 6? Okay, let's do it. This is an even number, so this bit is 0, and then 4 plus 2. Okay, this is this. No. Oh, wait, this is like, wait, was this like Little Endian or some stuff like that? No. I love how they say as the list. This what I just also said here. No, try again. Okay, so I would not come to the conclusion that it works like this now. The 0 at the front mean, oh, what? I'm not sure from which direction I'm reading this now. Zero plus 1 plus 2. Okay, from left to right. Oh, I was reading it from the wrong direction all the time, or what? Yes, this seems very unusual. But actually, if a list is representing a number, then actually it kind of makes sense that it starts at the front of the list. Yeah. Yeah. Yeah, funny. I have to. It's funny. I wrote down these, but they don't mean what I was thinking. I need to update my. I'm seeing them in a new light. Suddenly, it's from left to right. But yeah, of course, they're funnily enough, they were palindromes, or this is called. How do we represent 19? Alright, okay, so 19 is odd. (16 plus 4). Okay, so I need to say 4. So this here was the 1, 2, 4, and then 8 and 16. Like this. This should be 19. Maybe I'm wrong. Oh, wait, this is not 19. I'm just wrong. A sec. I try again. Fuck. 16. Wait, 16. 16 plus 2 plus 1. 16 plus 2 plus 1. Yeah. And wait. So yeah, 16 plus 2 plus 1. Yeah, like this. Oh yeah, like this. This is correct now. How do we represent... One sec. Let me... integer to string would have been it. Okay, yeah, like this. Okay, and then the thing is, well, yeah, the reverse of this. Okay, so the reverse of this. Fuck. Okay, there you go. Correct again. What is interesting about the lists that represent the numbers we have seen? They contain only zeros and ones. Yes, what else is interesting? Every non-empty list ends with a 1. That's true. Doesn't make sense to add another 0. Does every list represent of a number end with 1 except for the empty list which represents 0. Compare the number that represented by n and oh that's cute. Okay, n and a list 0 and then n. This is n. Okay, wait 1 sec. That is n. Yeah, n times 2. Damn, this is cool. But n cannot be the empty list since this with the empty list is 0, which does not represent the number. That would just be 0. Yeah, that's true. But 2 times 0, yeah. Well, yeah. Why is this not a number? This could just be 0 and be fixed. Okay. If n is this, then what is this? Well, it's prepending a 0. That's since twice 5 is 10. 2 plus 8. Yeah, 2 plus 8. Yeah, true. Compare the numbers represented by n and then 1 n. That means times 2 and then plus 1. 1 more than twice n. Even when it's the empty list. True. 0 plus 1. It's 11. What is the value of build num 0, the empty list? What is the value of build num 36? Yeah, the outcome of this. Okay, define build num. Okay. Guess I had it coming. Okay, I leave it for now. See you on another day, my friends.